Right. So before the interruption, what I kept on explaining is the points that we were covering in the last two sessions, and the final part was about time domain and frequency domain. That those are just signal graphical representation methods for further analytical purpose, right? So let's make the recapping stop at that point and let's continue. So in this section, signals part 2, what we are going to discuss is composite signal, or you further call it complex signals, right? Not simple. Now, in the last session, what we were referring to always is a simple signal, just a sinusoidal signal with a single frequency and some sort of a constant velocity, voltage and phase, right? And phase. Right. So the discussion is about complex signals. Means not simple as you saw previously. There are differences in frequencies, there are differences in amplitude, sometimes differences in phase. So when it comes to complex signals, you see different variations in all these important parameters. That is how a simple signal and a composite signal varies. If someone asks you what is the difference, in a simple signal always you see limited variance in the parameters, but in composite signals what you see, all the parameters are having complex values, always variance, right? So let's see further, let's go further and see what are the things we have to discuss. So here, this is just to recap the last slide that we kept on discussing in the previous lecture. This is where we stopped. The time domain and a frequency domain of sine waves. And here you understood we were just referring to two simple sine waves. The other is of 5 volts, the greater one is 10 volts. And the frequency is also different. The green color signal has a greater frequency, and the pink color signal is having a less frequency, which is 8 cycles per second, and the other one is 16 cycles per second. So you see that on the frequency domain graph, x-axis is frequency, and we just have a vertical straight line to represent the wave component right on top of 16 hertz, which is having a height of 5 volts when it comes to amplitude, and 8 hertz on top of 8 having a height of 10 volts. And this is a special case we kept on discussing about direct currents. You call it, when it comes to signals, you call it the direct current component, right? AC component, DC component. That is the technical way that you are always expressing these two cases, AC component, DC component. So this is the DC component, doesn't have a frequency. It's DC means the constant value is constant. When it comes to a constant value, you don't have a rate of change. Rate of change is 0. That means frequency is 0. But it still has an amplitude or a voltage. So we can still represent DC components on frequency domains as well. Because time domain, it's no big deal. Everybody knows how to represent or how to present, or how to draw, how to plot a direct current component. But in frequency domain, always direct current components comes on top of 0 hertz and having a particular height appropriate to whatever the amplitude. So this is what where we stopped at the last discussion. So let's go further and see what we have to discuss today, which is new. A single frequency sine wave is not useful in data communication, right? Now, first of all, in this sentence, to understand the message comes with this statement, you need to be clear with data communication, right? Because it says the single frequency. You know what is single frequency by now? It's a simple sine wave has a one frequency. A single frequency sine wave is not useful in data communication. So the main point comes here with this word, this part, data communication. Data communication is also a general term. So the main point is data. You need to be very much clear with data. What is data? You use the word data to represent information in the digital domain, in the digital platform. Okay. uh, some books, especially Americans, they for analog even they call analog data, right? But in the British English system they call it information. When it is analog they call it information, but Americans they call it data. But the right way to understand without having confusions as Sri Lankans, right? We need to learn from both. Data is used for information in America, so they don't care whether it is in the analog platform or the digital platform. They simply call it data. Why? The reason is nowadays we have no concern whether it is analog or digital. End of the day, everything is in the data platform, in the digital platform. Even now, I am talking to a microphone, right? I'm talking to a microphone. Long years back, like in the olden days, what happened was, if I want to convey some message, I have to use only the telephony system. So if I want to talk to you like this, I have to do it individually. To pass this message, I have to take individual phone calls to every one of you by using a landline. That means a cable telephone system. You call it the ordinary telephony network. It is quite analog. All the signals conveyed all around the networks are analog those days in the beginning stage. Then year by year the development comes, more research, and all these telephonic networks converted to digital. So in the telephone set, what happens? When we talk to the microphone, they take the analog signal and convert to digital, and then keep on transferring all around the network until it goes to the other telephone to listen by the other person, right? So normally the voice was analog, and from its nature, voice is analog because it's pressure waves coming through the air medium, and the microphone diaphragm keeps on vibrating. It is quite analog, and it produces an electrical signal, electrical representation of a pressure wave in the same frequency, but it is also analog. So this voice is analog, but nowadays in the current situation, doesn't matter, the voice is analog. It is to be analog only until it goes to the computer, only until it goes to the device, goes to your mobile phone. Right at that point it starts acting as digital signals. So Americans think in that way, and they say whatever it is, they don't care, everything is data. End of the day, everything is in digital platform, in the format of digital. End of the day, so they regardless of worrying about whether it is analog or digital, they call it data. But English, what happens is, they are used to their whatever the tradition, so they say analog or ordinary things, information specifically generated or specifically modified set of information, you call it in the digital domain, they call it data, right? So I want you to be clear with this background information. And especially what I am mentioning here is data. Mentioning from the word data here is digital platform. So single frequency sine wave is not useful in data communications. That means just a single sine wave, single frequency sine wave cannot be used to interpret digits like ones and zeros. You know that to interpret the logic 1 and 0, right, to insert logic 1 and 0, The signal needs to be discrete, somehow having some constant voltage levels, a high level and a low level. So then according to high level and low level, we can assign digits. Once you assign digits to these levels, once you assign a logic to these levels, you can call it digitized or digital. But how come that we use a sine wave which is having a constant variation all around the range, all over the range? The voltage keeps on continuously varying. There is no any discrete levels. So in a natural case like this, it's really hard to interpret a logic like 1 and 0 binary logic එකක් දාන්න අමාරුයි. මේකේ value එක continuously change වෙනවා. Continuously change in the value එකක් අපිට assign කරන්න බෑ constant value එකක්. So it's unable. That is the meaning of this statement here. A single frequency sine wave is not useful in data communication. Just a single. So we need a solution for that. Data communication means digital communication or communicating digits, communicating ones and zeros, right? That is what we call data communication. Let's say you all are listening to a radio station through FM radio, right? Just a receiver, you're tuning your FM station for whatever a channel that you like, and you're listening to music. That is not data communication. That is quite analog communication, right? So they are going to take all the information, the songs, the speech, the advertisements, everything. They're going to play all of them in a audio system, and they link the audio system with a transmission system, and through the transmission systems they use antennas to do the broadcasting, propagation all around the area or the country. So we who are having the receiving sets, if we can tune the station, letting the frequency resonated by our tuning circuit, we will be able to grab that signal and listen to the music. This is quite analog. So you don't call those type of scenarios data communication because it's quite analog communication. Normal television that you all are receiving through antennas, not POTV communications, not satellite communications, but the other ordinary television, telecasting systems, those are also analog, right? Because we receive everything through antennas, and it is quite what you call electromagnetic radiation and quite analog. But internet, Wi-Fi, then GSM, data through GSM system, mobile data you call it, SMS, MMS, those type of communication mechanisms, if you take, those are data communication, especially internet. Now we all are getting connected to this session in all around the country. I don't know where you live, but hopefully in different places, not in the same place. But we still we are getting a chance of connecting with this session. That is with the help of the internet system, the networking system. But all the information conveyed all around this network is binary, in the binary format, or you can call it data. So this is a data communication aspect, right? Single frequencies are not useful. Then we have to look what sort of sine waves or what sort of waves do we need for data communication, or what sort of waves which are catering the requirement for data communication. So here it says we need to send a composite signal or a complex signal, a signal made of many simple sine waves. Now I hope with this statement you get a clue, you get some understanding. What is a composite signal? We need to send a composite signal, a signal made of many simple sine waves, right, to cater the requirement of data communication. Just a single frequency sine wave is not useful or is not enough to fulfill that requirement, but a composite signal which is made of several simple sine waves can be used for data communication. That is the understanding that you need to take from these two statements. Okay, so composite signal or complex signal is a combination of many simple sine waves, right? Combination of many simple sine waves. That is the understanding you need to take out from this slide. Now here you have a simple graphical support given or a picture given to understand how a basic complex signal or a composite signal looks like. So when it comes to composite signals also, we have two categories: periodic composite signals and non-periodic or periodic composite signals. So here what you see is a periodic composite signal. Now forget about the composite nature. Think about periodic and non-periodic, because you kept on learning that two properties. How come that we can say this signal is periodic? The reason, you see, here we have somehow a particular shape on the positive domain, right? Then in the next instant, you don't get the same shape in the positive domain, but you get a shape in the negative domain. That means, then again, uh, right after finishing that pulse, you again get a shape similar to the previous one in the positive domain. Then again, the negative domain, there is a pulse similar to the previous negative one. That means from this border, you can separate a one wave component, because you see the same thing occurs again and again. So you are going to identify a one wave component, a positive cycle, a positive half a cycle and a negative half a cycle, or a positive pulse and a negative pulse, both together as a one component. Then you see the same component with same dimensions, with same height, with same wavelength, or you can call it the period. You see the same thing again, and for the third time also you see the same thing again, which is maintaining the time span constant and the height constant. So these sort of waves which is having this nature, you call it periodic. The same wave period, capital T, occurs on and on, and the dimensions are also the same. So this is a periodic signal. Then how can we call this composite? Composite periodic signal. Yes, this is periodic, but not simple. It is composite. Composite means complex. You see, if it is a simple sine wave, how do it looks like? It just keep on gradually increasing, goes to the peak and come down, gradually decreases, then go in the negative direction, increasing and decreasing, increasing and decreasing. That happens in a continuous manner. But in this complex signal, what do you see? When it comes to the peak range, when it comes to the peak point, the peak of the simple sine signal is also having a variation. Peak is varying. Here you can see the peak value keeps on varying. There's a fluctuation. Then you see the same variation, same rate of the peak variation occurring in the negative domain. The rate is the same. Then again in the next cycle, positive domain, the peak changes, fluctuates in the same rate. Negative domain, the peak fluctuates in the same rate. Again in the third cycle also the same. So this sort of an application or this sort of a signal, you can call it complex, because you don't see that there is a one single peak value. The peak value keeps on varying. That means the peak amplitude as a parameter is varying, right? Peak amplitude is varying. Voltage is varying, as well as the peak amplitude is also varying. What is the rate of that variation? Now here you see the peak amplitude is also having a sinusoidal variation, right? The variation is sinusoidal. This variation is sinusoidal. That means this is also a vibration. You have a bigger vibration with less frequency and larger amplitude, bigger vibration. On top of that, you have less amplitude, high frequency vibration. So that high frequency vibration is making the peak amplitude keep on vibrating in the same rate. This is the meaning of this picture. Let's go further, step by step. You will further understand what's happening. But just to make you deal with this concept, I just wanted to explain this picture so that to make sure that you somehow know something about this picture, right? Try to memorize a sign with the different colors, just imagine that you are drawing something like that. So you get a simple sine wave in green color. It just go up and come down, just a one peak value. Then it goes down to the negative direction and come up, just a one negative peak. Then again like that. So that's a simple. But this time you see the peak value keeps on varying sinusoidally with a greater rate. That is what you need to understand. So let's read and see whether I miss anything. Figure shows a periodic composite signal with frequency f. This type of signal is not typical of those found in data communications, right? We can consider it to be three alarm systems, each with different frequency, and analysis of this signal can give us a good understanding of how to decompose a signal, right? Now this is a three alarm system. The meaning of three alarm system is we will be having an alarming system works with three different tones, three different frequencies. That alarm is emitting a sound or outputting sounds with three different tones. That is what you call three alarm systems. The three different tones are based on three different frequencies. So your whatever the supply that you give, input that you give to the alarm system is having three different frequencies. So this is a complex signal, a periodic composite or a complex signal. Here it says this is not even much suitable for data communication. Why is that? Can someone answer? It says this type of signal is not typical of those found in data communication. In data communication, there are complex signals. But what you see here in the red color lines, with the red color lines, is not still matching with the complex signals we see in data communication. So that I can say this red color complex signal is still not fulfilling the requirement of data communication. Can someone say why? Can someone reason it out? You don't want to have a mastering knowledge to answer that question. Just the things that you have learned so far is enough. Why even this complex signal is not suitable for data communication? Even though it is complex, still not suitable. Reason? I want you to answer. Someone is typing. Need to be single frequency for more clarity? No, no. If it is a single frequency, it is not suitable at all, right? Yeah. uh, it's a continuous signal. Yeah, you just came a little bit near. Need to be a single frequency for more clarity? No. The problem with this signal, now try to understand data communication. That's why I just wanted you to be clear with the term data. Data communication means communicating binary digits or digitized information. So to interpret binary digits, there is a logic. That's what you were learning in digital electronics. You work with the logic. To interpret a logic into a physical system, that physical signal or the system needs to have some, some qualities or some features. So here, this appearance or this nature, the physical nature here is not fulfilling that requirement. To interpret a logic, always we need to have constant levels, right? We need to have clear constant levels. So here you don't find clear constant levels. Someone said that it's still continuous. Yes, even the peak value here keeps on varying, and it is also continuously varying, whereas the entire low frequency, the principal signal is also keep on continuously varying. This is still sort of a continuous or analog type of a complex signal. So if we can think about uh, just trimming all these, high frequency components, or just making it equalized to an average flat value, if we can flat this edge, that will be suitable for data communication, because we have a flat edge uh, and a negative flat edge. So we have basically two levels that we can interpret ones and zero logics for it. So you have a dotted line representation here. If we have a signal, complex signal, which is having some sort of a square shape outcome, that sort of a complex signal can be used for data communication, because we can easily interpret the logic, right? So if you are explaining based on the question that I asked, you have to explain it in that way. Okay, data means digitized information. Digitized information is based on binary logics. To interpret a logic into a physical system, that sort of physical system needs to have constant levels. So since this red color wave doesn't have constant levels, it is hard to interpret the logic. So therefore, this composite signal is not suitable for data communication yet. So if you want to make it suitable, what you need to do is find a method of uh, trimming and flattening the edges. So if you have a flat edge with many levels, then you can make use of those type of complex signals for data interpretation. Okay, so hope you understood some ideas from that discussion. So let's go further. If you are having questions, please ask. Time to time I'll check the chat box. Yeah, anyway, appreciate all your tries, Jaivi and Sanji, no, Sanji, Sanjay, no, anyway, right. Sorry if I'm spelling wrong. Right. Decomposition. Here we have another point. The analysis of the signal can be give us a good understanding of how to decompose a signal. And it is talking about a three alarm system I was telling you. Three alarm system is basically operating with three different frequency electrical signals. So based on three different frequency electrical signals, we used to drive three buses in three different tones, three different frequencies, right? So if you take this sort of a complex signal and decompose, when you are mixing simple signs together, means you are composing. So you say composite or composite, right? Composite. Some people spell it like that. Some cases spell composite. Whatever it is, you are composing, right? You are composing. Composing means mixing raw materials together. Decomposing means again going in the reverse direction, just reasoning it out, just splitting the ingredients, splitting the material into pieces, or scattering the material into pieces. So you take a complex signal, you can see here, as you can see here, and when we decompose, you will find how many simple sinusoidal signals are there, or if we are having a direct current component, what is the direct current component. Likewise, we basically do the decomposition. So in signals and systems, I don't know whether you have started it yet, but there is a mathematical lesson that you all are learning about decomposing a square wave or decomposing a composite signal. So in that lesson, you will be learning this statement: decomposition, decompose a signal. You take a complex signal like this and you mathematically decompose it with the values that you can read from this original signal. You do some, mathematics, Laplace transformation maybe, or some calculus, and then you, especially with the help of trigonometry, you can decompose it. So once the decomposition happens mathematically, you get different coefficients, answers, which describes the frequencies of other simple sine waves, the amplitudes of other single sine waves, and if there is any phase differences, you can see all these phase differences through the angle parameters in those mathematical representation. So in signals and systems, don't forget that you will be learning the other side of what we are discussing today, right? So here it says decomposition of a composite periodic signal in the time and frequency domains. Now assume if we decompose this, right? I'm going to graphically explain everything because I want you to understand the concept of this, because you are getting another solid chance of mathematically understanding this, but concept to the mind goes first is much more important. Then only you can deal with the mathematics and feel what is going on. So try to get the concept understood. If you are having any problems, any questions, please interrupt the discussion in the middle, disturb me, and ask the questions on the spot without keeping it with you till the end. Right. So if we decompose, now I hope you understand what is decomposing means. කෑලි කෑලි වලට ගලවනවායි රිවර්ස් අපි කම්පෝස් කරන ඔක්කොම එකතු කරලා ඩීකම්පෝස් කියන්නේ අපි එක ස්ප්ලිට් කරනවා ආයි ඔරිජිනල් condition එකට. We are going to split or scatter it backwards to take the original let me say ingredients or original factors that we were using to construct this. So if you decompose this red color signal, these are the components you get, right? These are the components you get. So here you can see that we have three frequencies. If you can see mouse pointer going all around, we have three frequencies. Frequency with value 3 times f, frequency with value 9 times f, right? So f, 3f and 9f, three different frequencies. Right, so here we have the great amplitude low frequency wave or signal represented by pink color, right? Frequency is f. Now here, if you think about this one wave component, right, just a one wave component of a pink color high amplitude wave, within that time duration, within the period of the bigger wave component, how many blue color wave components you have? See, we take a one big pink color wave, just a one cycle. Inside that one cycle, how many blue color cycles you have? Let me count. 1, up to this point, one cycle, then the second cycle of the blue color wave and the third cycle. So you see, within a one period of the main signal f, right, within a one period you get 3 cycles of the blue color signal. So assume that this position is 1 second, this position is time 1 second. So if it is 1 second, f is equal to 1, because we have only a one component within a second. F is equal to 1, 3f is equal to 3, because 3 times 1. Inside the same period we have 3 waves, so that is why you have 3f. Okay, 3f. Black color wave, the smallest amplitude, within a one wave component, see how many black color waves you have. 1, 2, 3, 4, 5, 6, 7, 8 and 9. So up to that point you have 9 smaller wave components. Frequency is high, 9 times f, right? 9 times f. So here students, that is how we normally read this, right? We normally read and understand. So one bigger wave and 3 times of that frequency, the intermediate frequency, the middle frequency, and 9 times of the original frequency is the highest frequency we get. So lower frequency, intermediate frequency, high frequency. Hope it is clear with you. Mixture of these three wave components, when you are electrically mixing these three wave components, which are all in phase, you can see the pink color phase angle is 0. Starting wave position is 0 degrees or 0 radians. Blue color starting position is 0 degrees or 0 radians. Black color wave, which is the high frequency starting point, is 0 degrees. Right, starting wave position is 0 degrees. So all these three waves are in phase, no any phase difference. The only difference here you can see is the peak amplitude keep on reducing when the frequency is getting higher, and frequency is increasing from one specific value to the upper value. So here, students, 3F or this blue color intermediate frequency is based on F. F means the first frequency. Then if you go to the highest frequency, it is 9 times the original frequency. Second one is 3 times the original frequency. Third wave is 9 times the original frequency. Therefore, you can understand that, you must understand that second wave is a multiple integer multiple of the first wave frequency. Second wave frequency is the third integer multiple. Integer, what are integers? Negative positive whole numbers. You call them integers. Not decimal numbers, but whole numbers. Positive 1 to positive infinity, negative 1 to negative infinity are respectively positive and negative integers. නිකිල සංඛ්‍යා, ධන නිකිල සංඛ්‍යා, ඍණ නිකිල සංඛ්‍යා. ධන එකේ සිට ධනානන්තය දක්වා ඍණ එකේ සිට ඍණානන්තය දක්වා ඇත්තේ මොනවද අපි කියන්නේ integer values, integers. So here you see the blue color second frequency is the third integer. Third integer, තුන්වෙනි නිකිලය, තුන්වෙනි ධන නිකිලය, third integer multiple of F or the original frequency. High frequency black color wave is wave frequency is 9th integer multiple of the first frequency. Therefore, what do we call the first frequency? We call it the fundamental frequency, right? Just F is given a name. We call it fundamental frequency, right? Don't forget fundamental frequency. Okay, right. So fundamental frequency is the bigger wave, that is the base. You call it the base wave component, and you have the integer multiples of the base wave. That means the frequencies. So since the original wave is called the base wave is called the fundamental, integer multiples of the fundamental are known as harmonics, right? Harmonics. So we have the third harmonic and the ninth harmonic. So if someone asks you what are harmonics, you should say integer multiples of the frequency of fundamental signal. Integer multiples of the frequency of fundamental signal is what we call harmonics, right? So if you mix a fundamental signal with its harmonics, what you get is something like this. Okay, so you have to make sure that you take a single low frequency and use of its fundamentals, mixing them electrically in an electrical mixer, right? You can simply electrically mix them by parallelly connecting all these together electrically. So you get one electrical signal, stay on top of the other electrical signal, then again another electrical signal, all are going to stay on top of each other in the same time span, as you can see here in this graph. But when you send this to the oscilloscope to observe, after mixing three electrical signals, the final output, if you send it to an oscilloscope and observe, you don't get a chance of observing something like this. මේ වගේ observation එකක් හම්බෙන්නේ නැහැ, separating the three waves nicely. What you see is something like this, right? oscilloscope will show, will give you an outcome through the screen, which looks something like this red colorway. So these are we call complex signals or composite signals, is because we use several simple sine frequencies, mixing them electrically, uh, and letting it compose a different appearance. You call it composite signal. So when you decompose it, again you will be getting these three wave components separately. So this is how we draw it in the time domain. If you switch to the frequency domain, you can draw the three frequencies by taking its peak amplitude value and appropriately the lines on top of each position. So fundamental frequency has the greatest amplitude. The third harmonic, which is the integer multiple of the fundamental, has the intermediate height amplitude, and the lowest amplitude is the highest frequency, ninth harmonic of the fundamental. This is how we represent a complex signal in a frequency domain graph. Unfortunately, here you don't find any. Fortunately or unfortunately, here we don't find any direct current component. No any direct current, so you don't see any representation here. It's just the y-axis. Right? Clear? So that is it. So when you mix, you get a different appearance like this. You call it composite. Any questions up to now? Any questions up to this point? Just want to check whether you all are with me. Right, there's a question. If it's times f, shouldn't the pink bar, shouldn't the f pink bar in the bottom graph do all the way to the left? Go all the way to the left. Jaivi, your point is not clear. Jaivi, point clear nahi mata. If it's times f, so give me a second. Okay, yeah, no problem. How about others? Still Jaivi comes with the question. How about others? Any questions? Anything? Any clarifications regarding the things we discussed so far?
Hi, sir. Can you hear me?
Yes, Jaivi.
I'm sorry, I had to switch to the phone because my mic's not working in the desktop.
Right.
I just want to know if it's by frequency f.
Yeah.
As in, if it's multiplied by frequency f,
yes.
Shouldn't the f go all the way to the left of the graph?
No, we are not multiplying f from f. What we do is we multiply f from 1 as the first integer. Right?
Okay, so in
clear?
The graph, the f is where the f bar is, it's regarded as 1. Is it?
Yes, 1 in the sense now like this. Now let's say first thing what we get is the base. Forget about the blue color and black color. Assume that you have only the pink color wave, right? And we call it the base wave or the most fundamental wave. Then if you want to construct or compose a complex signal, what we do is, if we need a periodic one, right? So here what you see is a periodic composite signal. So if you need a periodic composite signal output, what we have to do is we have to make sure that the other frequencies that we are mixing are integer multiples of the fundamental frequency that we are selecting. Okay, so we take the first major frequency f. The first integer we get from maths is number 1. So if you multiply f from number 1, you just get f. So there is no point of discussing about the first harmonic. First harmonic is always the fundamental frequency. Okay, is that clear?
Okay, yep, that makes sense.
Right. Yeah.
Thank you.
Okay. Then what we do is when we go for higher integers, like third one, the fifth one, the seventh, or odd numbers, or what we call them even numbers, right? 2, 4, 6, 8, 10, or 3, 5, 7, 9, 11. Likewise, we can take odd numbers or even numbers and take integers, multiply, and let them mix together. Okay, so the main thing what we have to do here is identify a base. First, a low frequency base, and make sure that the base is periodic. If it is an unperiodic one, definitely the outcome will be non-periodic. I will show you some non-periodic composite signals later on, but that is after being clear with exactly what is a composite signal. Then we can do modifications and learn different applications. So here, if you need a periodic composite outcome or a complex outcome, definitely the base have to be periodic and low frequency. Here, the pink color one is the base, which is a periodic signal. You can see the same appearance comes again and again. And the period of the base is the same all around the 3 cycles here. So it's a periodic, low frequency base. Theoretically, you call it the fundamental frequency. The fundamental frequency. Then, from the concept we know, if you need a proper uh, like periodic complex signal outcome, which is having the same dimensions or the same period maintaining on and a well structured complex signal outcome, definitely we have to take the fundamental frequency, take some of its harmonics, that means higher integer value multiples, mix them together. So here in this example, we have chosen the third one and the ninth one and mix them together so that you will be getting something like this. Okay, other than that, there is nothing here to discuss. This is not about shifting the wave. What you were exactly explaining, Javi, is a different concept. That is what happens in modulation. You call it frequency shifting, right? Frequency shifting. You take a fundamental frequency and you multiply that frequency with another frequency. Then automatically what happens is your original frequency is going to be superimposed in another spectrum. That is a completely different story. So here we are not multiplying f from f, but we multiply f from an integer value, right? Integer value. So don't misunderstand that we are not going to multiply frequency with a frequency. That is happening in a different aspect. You call it modulation. This is too early to discuss all those. When we get a chance, if we get a chance, we'll do it. Or otherwise, as I was telling, people who are mastering communication or radio communication, they are learning this. Anyway, I'll try my level best to teach something for you within this semester. Let's see how time permits us to do that. Anyway, I want you all not to misunderstand with modulation and this sort of wave constructions. Here what we do, multiply the frequency with just numbers, just integer numbers, not a frequency with another frequency. So if you are multiplying a frequency with another frequency, definitely, as Jaivi said, the wave starts moving, shifting from either to the left direction or the right direction according to the value. But here none of those type of things happening. We just multiplied from integer values, right? Integer values. Okay. Any more questions regarding that discussion? Others? Others are so silent. I don't know why. Anyway, let's continue if you don't have questions, but if you have any, please interrupt and let me know. Right, so now here we have the summarization of the previous discussion. Composite signals, F is called the fundamental frequency or the first harmonic. There you go. Fundamental frequency and the first or the first harmonic. How come the fundamental became the first harmonic? You call F the fundamental is for a reason. Why? That is the base. That is the base frequency. That is the original frequency that we are using. So you can call it the fundamental. How come the first harmonic became the fundamental? or how that we call the first harmonic or the fundamental, the first harmonic is a simple mathematical solution or a justification. If you take the first harmonic, the meaning of the first harmonic is you take integer value positive 1, the integer positive 1, and multiply f from 1. So when you multiply f from integer value 1, you get f as the value. But because of that mathematical operation, conceptually we can call it the first harmonic. Conceptually that is the first harmonic because we multiplied from integer number 1. So multiplying from integer values, fundamental frequency multiplied by its integer values, you call it harmonics. So first harmonic is multiplying the fundamental with first integer. So if you do it mathematically, you can call it first harmonic. Therefore, there is no problem in calling the fundamental frequency first harmonic or the first harmonic the fundamental frequency. සිංහලෙන් කිව්වොත් ෆන්ඩමෙන්ටල් කියන්නේ බේස් එක. මේම බේස් එකක් අපි හදා ගන්නවා ඉස්සෙල්ලා බේස් ෆ්‍රීකවන්සි එකක්. and we are making sure අපි ඒක make sure කරනවා මේ බේස් ෆ්‍රීකවන්සි එක periodic. ඒ කියන්නේ same period එක maintain වෙනවා. and constant peaks, right? Constant peaks, simple sine wave එකක් low frequency high amplitude. ඒකට තමයි අපි fundamental frequency කියන්නේ. ඒක තමයි base එක. අපි ඊට පස්සේ කරන්නේ එයාගේ frequency කරගෙන ඒකේ ගුණිතයන් හදා ගන්නවා. හරි ධන නිකිල ගුණිතයන් හදා ගන්නවා. ඒ ගුණිතයන් හදාගත්තම ඒකට අපි කියනවා harmonics කියලා. හරි. මට සිංහල වචනේ මතක නැහැ. අපි ඉස්සර physics කරපු අය දන්නවා practicals වලට අපි මේක කරනවා. We do it in physics practicals. Honestly, I cannot remember the singular term of it. පළවෙනි මොකද්ද දෙවෙනි එහෙම කී අපි කරනවා first harmonic second harmonic. Likewise we were doing a practical. පළවෙනි උපරිතාණය දෙවෙනි උපරිතාණය පස්වෙනි උපරිතාණය, just a study of vibration. We were doing it in physics. If people who have done physics here in this forum, they must know. They can remember what you did in practicals. So same thing happens here. We call it harmonics. අපි ඒවලට කියනවා harmonics කියලා. උපරිතාන වලට කියනවා harmonics. ඒකට harmonics කොහොමද mathematically derive කරගන්නේ? අපි ධන නිකිල සංඛ්‍යා අරගෙන වැඩි කරනවා fundamental frequency. එතකොට f කියන එක අරගෙන ධන එකෙන් වැඩි කරොත් අපිට ඒ වැඩේ කරපු වැඩේ නිසා අපිට ඒක කියන්න පුළුවන් first harmonic කියලා. ඒතර automatically first harmonic එක සමානයි fundamental එකට. එතකොට අපි ඒ වචන දෙකම අපිට පාවිච්චි කරන්න පුළුවන් base wave එක හඳුන්වන්න. So that is the single explanation I can give about that. Second point says 3f and 9f are the third and the ninth harmonics of the composite signal respectively. Third and the ninth harmonics are 3f and 9f are the third and the ninth harmonics of the composite signal, right? So in this composite signal we have the third harmonic and the ninth harmonic based on the fundamental. Okay, so mix them together, you again get a frequency like this. So I hope now you understood something about harmonics and fundamental frequency. This is also very important. So when it comes to your signals and systems module, when you mathematically decompose a composite signal, again I'll repeat, you are going to decompose කෑලි වලට ගලවනවා composite signal එකක් අරන්. හැබැයි ඒක ගලවන්නේ not from screwdrivers or any other tools, you do it from mathematics. So mathematically when you differentiate it, you will find different other frequency components. ඔයගලන්ට හම්බ වෙනවා harmonics වල frequencies values ටික. You will be getting the different frequency values of the harmonics. Then you will again you are getting another important parameter, which is the peak value of all these different frequencies, different harmonics. And if there is an angle phase difference, you will be getting a theta value appropriate to all these derivations. So to decompose karnona mathematically, you will be getting theta values, alpha, beta, gamma, whatever it is, anyway, and angular values if there is any. If all these harmonics are in phase, you don't get any angle values, so you can conclude that since we don't have any angle values derived, angles are 0, that means all the harmonics were being mixed are in phase signals, no phase changes. So that is over. Then you go to what do you call this? The frequency component, right? Frequency component, you will be getting different values. Then after all, you can find out what are the integers, integer multiples. So what are the harmonics? What harmonics are there? Then the amplitudes, the peak amplitudes. Okay, so this is what happens in that module. In this module, I am just giving you the concept. So now you have the base, then you mathematically do all the derivations by having this base understanding with you. So that is my main objective of delivering this session. I hope you are getting the exact point as I'm thinking. If you are having any doubts, මම මේ කියන මලදානේ තේරෙන්නේ නැත්නම් කරුණා කරලා අහන්න. Please, right? Please interrupt and ask. Now here this is just one example of all these statements. And here you have on top, you have the definition of a harmonic. Harmonics are integer multiples of the fundamental frequency. So if you select a fundamental frequency, if you select an original frequency, you call it the fundamental, and multiply it from the integers, you get harmonics. So here a small example. If the fundamental frequency is f, which is equal to 10 hertz, all of these are simple sine waves. All of these are simple sine waves, right? Fundamental frequency is equal to f, which is equal to 10 hertz. First harmonic, here comes the point. First harmonic is equal to fundamental frequency f times 1, integer value 1. That means 10 times 1, answer is 10 hertz. So you can see value wise it is the same. That means you can conclude first harmonic is the fundamental frequency, right? First harmonic is the fundamental frequency, so there is no problem. Second harmonic is equal to f times integer value 2, that means 10 times 2, 20 hertz. So the second harmonic is 20 hertz. Third harmonic is f times 3, 10 times 3, 30. Likewise, going on. And you can go to the nth harmonic in a generic way. Capital nth harmonic is equal to fundamental frequency times n, 10 times n is equal to 10 n hertz, right? So this is basically what we call harmonics of a particular fundamental. I hope it is clear. Any questions now with the harmonics? Any questions? Are there anything which is not clear for you up to this point? Yeah, Rakib, I can see that you're raising hand. Any questions, Rakib? Rakib, was it a mistake or you have any questions? You mistakenly press it or do you have question? All right, so it's a mistake. Okay, no problem. Okay. Right, so what I can do now, I'll just give you a 10 minutes break, right? Because now we are moving to the important part. So I want you to take just a bit of time to refresh your system. So take 10 minutes break. 10 minutes, now it's almost 20 past 2. So let's meet at 30 past 2. So you have 13 minutes break, right? So I will be again start delivering exactly at 30 past 2, half past 2. Okay, take a break and come. Then we'll discuss the rest of this. But during the break, don't try to lose your concern. We were talking about complex waves. Then you understood a periodic complex wave, how it looks like, and the construction part of it. You take a fundamental and you take some harmonics of it, mix them together, then you get a outcome as you saw in that red color wave. Then you understood what is a fundamental frequency, what is a harmony. So keeping all these points in mind, just go and have a break and come. Okay, I'll be starting again at 2:30. You almost have 12 minutes now. Okay, enjoy. Okay, hope you all are back after the breaks. Right, so let's continue with the rest. So let me share the screen. Right. So we were here. Let's move one slide further and see what is the next thing that we have to discuss. Right. So there's a note given. According to Fourier analysis, Fourier is a mathematician who came up with a specific mathematical derivation method, which is to be used for decomposition purpose of complex situations, complex systems. So basically, when we are in a position of mathematically decomposing a signal and a system, which is having the composite nature, we can make use of the theories introduced by the mathematician Fourier to get it done. So you call it Fourier analysis to credit the founder of this mathematical content. So you call it Fourier series or Fourier analysis. So in signals and systems, what you are doing is this Fourier analysis, making use of this Fourier series to analyze by decomposing a complex signals. So according to Fourier analysis, any composite signal is a combination of simple sine waves with different frequencies, different amplitudes and different phases, right? So this is a statement giving you statement given actually to summarize what you were learning so far, and just an introduction to the point that we are going to learn next, right? So this is some sort of an intermediate type of a statement which justifies or which concludes everything you learn so far, and which gives you some sort of a intro to the next bit you are learning. According to Fourier, now if you do decompose through mathematics and see, you will find that all the components you get after the decomposition or through this Fourier analysis is representing all the harmonics, the frequencies of the harmonics, the relevant amplitudes of the harmonics, as well as the phase. If there is a phase change, that will also be there. Now, next bit, I will be showing you what is the Fourier series looks like. Then I'll explain what are the wave parameters from its mathematical point of view. Now, in the first lecture, signals part one, I was just conceptually showing you what are the wave parameters. Today I'm going to show you the mathematical aspect of the same content. So let's first see what is Fourier series looks like. So here you see the Fourier series, which is the mathematical representation of a general Fourier series, which we use to represent complex waveforms or complex signals. We use Fourier series to decompose any periodic signal into its harmonics. Same statement repeated. So here you see example, Fourier series. These are the components you see. I don't want to explain it now. Before everything, let me show you something else. So here we have a subject to this equation. Then we have a value here, A0, as you can see, A0. Then we have a series. N value will go from n to infinity. So for the n parameter here, the variable, you could apply values from 1 to infinity, which are positive integers. So here we have another parameter a n 2 phi nft, all are under the sine parameter or the sine function. Then we have another plus, a series, n is equal to 1 up to infinity. We have bn, and that time the trigonometric ratio is cos, and we have the same representation 2 phi nft. So here n value could be from 1 to infinity, again positive. So these are the things we can see here, but most of the cases are not clear. because you have no idea, most of you, I hope most of you have no idea uh, what are these for, actually what are these for, and what are all these parameters all about, right? So let's go and clear that part first, which is the fundamentals. So we'll clear that part first and then come back to Fourier series and see whether you understand all this, right? So what I'm going to do is I'm going to teach you some basics. Then I'll be giving you a chance of using that basic knowledge to figure out what is happening here. So that has to be done by yourself, right? So let's start. Now, before understanding the Fourier series, now here, if I show you, we basically have three components. People, you know that when it comes to an expression, now if you think about the right hand side of this equation, it's an expression. A0 plus uh, another expression here, then plus another expression. All together is a bigger expression. So in this bigger expression, you see that there are critical, you know, signature, critical mathematical signatures. In equations, you know, in expressions, you know, if there is positive or negative signatures, those are critical. So we can use positive and what you call negative signatures to critically divide sub expressions. So this A0 is critically divided from this part. Okay. Inside this you find a lot of multiplication. See, an times sine. Inside the brackets 2 times pi times n times f times t. Multiplication. Those are not critical. But this positive sign is critical. It is something like a wall between two lands, two houses, right? So it's a critical line drawn uh, to differentiate the two areas. So likewise, this positive sign is critically dividing these two parts. Then again you have a critical positive signature here to differentiate these two sectors. So you have sector number 1, sector number 2, and sector number 3. So three sectors. Okay, three sectors. One is a sine. One sector is based on the sine ratio, the other sector based on cost ratio, and just a constant value here. Then we have the subject on the other hand, other side. So let's see. Now that is what you can see from Fourier series. Let's go and learn some basics. Then we'll come back here in Fourier and try to figure out what is going on. Right. So what I want you all to make sure is whether you see the word on the screen now. I'm in the Word platform, Microsoft Word platform. Can you all see this? Is the Word platform visible, guys?
Yes, sir.
Right, good, thanks. Okay. Right, so if we come with a simple heading, simple function of a sine signal, right? Simple function of a sine signal. So if we take it like this, first I would type is equal to capital E let me take it as omega. Then we have theta, right? Omega t plus theta. Right? Hope everyone can see this. Right? Simple V is equal to E times sine within brackets omega t plus theta. Right? Omega t plus theta. When it comes to omega, right, if you can remember in physics you were doing angular motion, angular motion, angular velocity, angular acceleration, angular displacement, right? Angular motion, if something is rotating, if there is a mass moves in a rotational path, what is the frequency, what is the velocity? You call it angular velocity, because it always change the angle. So rate of change in the angle, angular displacement, you call it angular velocity. Rate of change in angular velocity, you call it angular acceleration. Those type of things you kept on learning during the physics season. Now, when it comes to that content, omega is what we call the angular velocity. Linear velocity is simple v, meters per second. Angular velocity is omega, radians per second, right? Radians per second. Because angular displacement is not measured in meters, angular displacement is measured in radians. So rate of change in angular displacement will be meters per second, not meters per second, sorry, radians per second. So omega, so far you know omega as angular velocity. In this case, omega is angular frequency. Okay, angular frequency. I'll explain omega. Give me a little time. I'll explain omega. First, let's be clear with what is omega. Omega is angular velocity. Right? Omega is angular velocity. And moreover, omega is equal to 2 times pi times simple f times simple t. 2 pi ft. Right? 2 pi ft. Therefore, we can again replace this omega here from 2 phi f. Sorry, omega is 2 phi f, right? Not t, 2 phi f. We are going to replace it from 2 phi f. Now here what you get is right, the sinusoidal signals mathematical expression. If you take a simple sine function, sinusoidal signal, this is the mathematical explanation. So let's be clear with what are all these parameters. Now why that we call it angular velocity? Angular velocity. That is because when it comes to exact physical motion, the mass starts moving in a circular path with a particular velocity. You call it angular velocity. When it comes to vibration, when it comes to oscillations or signals, What we always deal with is a vibration or an oscillation, and the main component when it comes to signal communication, the main component we are relying on is frequency. Frequency is how faster the vibration happens, right? Frequency is how faster a cycle will be completed. It is not about angular velocity straight away, right? But how faster one complete cycle will be one cycle will be completed. Within a second, how many complete cycles are occurring? That is the idea. So since this omega value here in this representation is based on 2 phi and especially f, which is the frequency, you call this angular, sorry, this is velocity, frequency. Angular frequency. You call this angular frequency because this is not based on displacement, right? This omega is not based on angular displacement, but the omega is based on the frequency. So that we specifically call omega, when it comes to signals, angular frequency. Don't misuse it or misunderstand. This is not angular velocity. But in physics, in physical motion, in dynamics, right? Rotational dynamics, that is angular velocity. But in signals, because it is dealing with oscillations, which is having particular frequency, this omega is based on frequency, so you call omega angular frequency, right? So when it comes to angular frequency, it can be further evaluated as 2 pi f. Now let's be clear with what is 2 pi. 2 is a constant anyway. What comes with this pi value, right? Pi is equal to 180 degrees. So pi in radians equal to 180 degrees. So how many of you know what is a radian? Anybody can define a radian? Can someone define radians? Can anyone define a radian? What is a radian? That is a one measuring unit of angles. Now we basically very much we are into degrees, right? To measure angles, but there is another way we used to measure angles, especially for physics we use it. Most of the physics laws and rules are based on radians. So it's another measuring technique, right? Measuring unit. So how to define radian? I'll just take it. How many of you know? Anybody knows what is a radian? If you know, no point of wasting time. Yeah, 1 pi is equal to 1 pi in radians is equal to 118 degrees. That's true, but my question is whether you know what is a radian. Definition of a radian. If you try to explain it, we are going out of our concern. Right, yeah, Jaiv is correct. Angles corresponding, one radian is an angle subtended at the center of the circle by the arc of the length equal to the radius. Very good, right? So here we have two explanations, simple explanations for others to refer. Jaivi and Sanjay. Then again, I can see Saneru is typing. That means average, you all know, right? You all know. If you all having further doubts, you can discuss with me later or else with among your friends. So you can be clear with that. So I don't want to waste time explaining radians now, right? Appreciate. Okay, right. So 2 pi in radians. Pi in radians represent a half a cycle, 180 degrees. So 2 pi means it represents a complete cycle. It represents a complete cycle, right? It represents a complete cycle. Angular frequency. Angular frequency means, now as an angle, a complete cycle as an angle, we take 2 pi in radians or 360 degrees, 316 degrees. So we take 360 degrees, multiply it from the frequency value. Multiply it from the frequency value. What is the meaning of that? Assume the frequency is 10 hertz. If the frequency is 10 hertz, what is the meaning of that? Within a 1 second, the oscillation is capable of completing 10 cycles. That is what we call frequency, 10 hertz. If the frequency is equal to 10 hertz, we can say that particular oscillation is capable of fulfilling 10 complete cycles within a second. 10 as a value. So how can you mathematically represent this? Because we were using examples, we were using English words, English grammar to explain this. But how can we mathematically write the sentence? This is the method of mathematically writing that sentence. 2 pi represents 360 degrees, so it represents a 1 cycle. Times f means times 10. That means you know 10 cycles. Omega represents the number of cycles per second, right? The value omega represents the number of complete cycles per second as a value. So this is how we mathematically understand this. 2 pi represents a cycle, f represents how many complete cycles within a second. So when you multiply these two, you get omega. Omega means exactly how much cycles measured in angles within a second. How much cycles measured in angle within a second, right? So this is an angular representation. So you call it angular frequency. 360 portions of angles. How many 360 portions of angles? That is what you call angular frequency, right? Hope that part is clear. Then when it comes to this equation, simple V, we call it the instantaneous voltage. Instantaneous voltage, I'll explain it later. Capital E, or let me make it capital A, because in that Fourier series we had A. Capital A represents the peak amplitude of whatever the sinusoidal signal, the peak amplitude value. Then we have the sine ratio, and within brackets 2 phi f, that means omega, times t. Simple t is the time of observation. Simple t is the time of observation, not capital T. You see here, you have simple t, the time of observation. That means within this omega represents how many 2 pi radians or how many 360 degrees portions are there within a 1 second. So 2 phi f means how many complete cycles within a 1 second. How many 360 degree portions within a 1 second. That is within a 1 second. Assume that you are going to observe 5 seconds. You are going to observe 5 seconds. Then within 1 second you get 10 360 degrees portions within 1 second. So when you are observing this continuous to 5 seconds, you have to multiply that 10 360 degrees portion per second with 5, then you get the total number of complete cycles or total number of 360 degree portions within 5 seconds. So this particular portion here explains exactly how much 360 degrees portions are there within a particular observation time. So end of the day, you see time here, you see a constant value, then a pi radian value, then a frequency value, or put them all together, the outcome is an angle. The outcome is an angle. 2 pi is equal to 360. 360 times 10, 3600 degrees. 3600 degrees times 10, 3600 degrees times 36,000 degrees. 36,000 degrees plus theta in degrees. Okay, so entire expression here within the bracket is completely an angular outcome. So sine angle, right? So you don't want to worry about this anymore by having frequency and time here. Even though you have a time component here as a mix, end of the day you get an angular outcome. So angle plus angle is an angle, sine angle. So what you have here, instantaneous voltage is equal to the peak amplitude and the sine ratio of whatever the angular representation, right? So this is basically explaining a sinusoidal signal. What is this instantaneous voltage means? Instantaneous voltage means, if I take you to a wave, right? Now think about this main bigger wave. What happens if you walk along the time axis? What keeps ticking is the time. First second, second, third second, fourth second. So the time keeps on ticking every second, every millisecond, every microsecond. So time keeps on ticking. So in each, assume in each millisecond, if you measure the voltage, you can see that voltage keeps on varying continuously. So every instant, every 1 millisecond instant, if you measure the voltage of this graph of this circuit, every instant millisecond you see different voltage reading. So for this all voltage readings, you call it instantaneous voltages. Why? Every instant voltage keeps on varying, so you call it continuously varying voltage. So for that you call it instantaneous uh, voltage. So now we easily use a language to express this idea. Instantaneous, what is meant by instantaneous, this and that. I'm using the language English to convey the message. How come that we convey the same message without using English but using the language maths? That is what happened here, students. That is what happens here. So this simple V represents that voltage variation. You are plotting a graph to represent every instant the voltage variation. So you call it instantaneous voltage. Instantaneous voltage, who represents the graph. So this parameter here as the subject represents the graph. Then you take the peak value and you show how this peak value keep on changing in every instant. How this peak value keep on changing every instant. Okay, so this is the idea of a simple sinusoidal signal, right? So I hope it is clear up to this point. Any questions up to this point, students? Any questions? Is that part clear with everyone? Right, so better if you are having an option to talk. I think it's better because we have to clear everything. If you are having problems, better if we have a solid you know communication method, so that everything will happen in a reliable manner. Anyway, so this is what happens with sine wave. So let me explain theta. Theta is the phase angle, right? So when it comes to the sine function, here this part represents how many cycles we have. How many cycles we have within whatever the observation time, and theta represents the phase angle. If you take an in phase sinusoidal signal, that means no phase changes, in phase, theta will be 0. Theta is equal to 0. But if theta is equal to some other value, that means we have a phase shift. Now, if you can remember the previous discussions, we were talking about phase shifting. In phase, half a cycle phase different, or that means 90 degrees phase different, 180 degrees phase difference, like that. So if you have a phase different, this theta will be getting a value. If not, if the component is in phase, theta will be 0. But anyhow, in this function, we need to have a parameter who represents the phase angle of the originating point, phase angle of the originating point, right? Okay, so this is it. If I take this part, here you have so here you have the so let me first draw a line. Right, then here we have capital A, right? This is capital A. You can see phase angle is 0, right? Simple T is the observation time. So let's cut this and take it for right. So here we have the sign. Now what happens if we have a phase change of 90 degrees, right? 90 degrees, what happens? Now don't forget, students, we need to be clear with cos, because in Fourier you saw that there is a cos component, cosine component, a sine component and a cosine component, right? So here now you see 2 phi ft, in between you have an n value. So now you are coming little by little near to the Fourier series. Now, but what we have is another cos component. So let's think about the cos and see what sort of a variation needs to be done for a sine signal in the case of identifying a cosine signal. So let's take the same topic further. Cosine signal, right? Simple function of a cosine signal. Now, if you can remember in trigonometry, what we were doing is let me first give me a second just to do some modifications. Right. So let me take this. First, we have to be clear with what's a sine function, right? So here you see a sine wave. This is a sine wave. How the cosine wave looks like? Just go to trigonometry those days and see what is the difference in cosine wave, right? Cosine function graph, if you can remember trigonometry at least a little, what's the difference? It is going to work in our way. We need to draw a line here. And make sure that the line is black and a little bit broader. So now here what you see is in the second picture what you see is a cosine function graph. So wherever you see this bit, that is the cosine signal. Alright, so this is a cosine signal. Everyone can see. The first one is sine, the second one is cosine. What is the difference? Right, I'm going to teach trigonometry now, but from trigonometry, if you just recap and see, go back in your mathematics and see, or at least just a little bit of Google to find out what is a trigonometric function graph looks like, and a sine function graph looks like, and a cosine function graph looks like, you will find this difference. But both are still sinusoidal when it comes to communication. In trigonometry, we call it sine, this is cosine, and there is a direct line that we separate. But when it comes to electronic communication, for us, both of these are still a sinusoidal signal. But because of a situation, we can mathematically separate these two, one as sine, the other one as cosine. Right? So let's figure it out. Now, this is a simple sine wave. You call it a simple sine wave, which is in phase. In phase, right? In phase. And in communication, as a wave parameter you were learning, phase is an important parameter. So in this second representation, you see the same wave. You see the same wave. What has happened? The wave has shifted, or you call it offsetted, to the left side. So in the initial position, in the starting position, wave has an angular position, angular value. What is the angular value? The peak value is 90 degrees. So the second wave, how can you explain the second wave? This second wave has a phase shift of 90 degrees. This second wave has a phase shift of 90 degrees. Okay, so this is in phase. Let me type. This is sine wave in phase. with 90 degrees out of phase, right? This is 90 degrees out of phase. Just a sine signal with 90 degrees out of phase. You don't call it a cosine signal when it comes to telecommunication or electronic communication. Please try to understand. Mathematically, yes, it is cosine. But when it comes to communication, for us, it's still sinusoidal signal. It is still a sinusoidal signal with 90 degrees phase shift. 90 degrees phase shift. Let me call it not out of phase. 90 degrees phase shift. It's the right term to use. 90 degrees phase shift. Okay. Sine wave with 90 degrees phase shift. So how to represent this in mathematical sentence? So you take this. Let's take the same example that we took here, and take it like this. 2 phi ft sine 2 phi ft. What sort of a modification that we can do to this? What sort of modification that we can do to this? So this theta angle, I told you, theta angle is the phase angle of the wave. Theta is the phase angle of the wave, right? Now in this equation, in this graph, what you have is a 90 degrees phase shift. Therefore, if you are trying to write a mathematical sentence for this representation here, the representation number 2, right? If we call this number 1, number 2, representation number 2, you get the original sign, but this bit here will become 90 degrees. Okay, will become 90 degrees. This bit theta becomes 90 degrees. Theta becomes 90 degrees. V is equal to a sine 2 pi ft plus 90. Okay, plus 90. That is what happens. Hope it is clear. So if you try to write the equation for this representation number 2, the first representation is just a pure sine signal in phase. So this is the equation. But second one has a modification, phase modification, 90 degrees phase shift. So how to represent that in a mathematical sentence is changing the theta value for 90 degrees. Okay, theta will become 90. Then still, now we understood that. But still in Fourier, if you go and check, we have cos 2 phi ft, no theta, but it is cos. But in this derivation, what you get, you understood, is still sine. Now, how come this sine becomes cos then? First of all, what I am going to do is I will explain the wave parameters here for your reference. Simple V is instantaneous voltage, right? Then we have capital A is peak peak amplitude. Then we have 2 pi take omega. Anyway, we have it here. Let's put that one here as well. Then we get 2 pi is a constant anyway. If you take pi, that is 180 degrees. So half of a cycle, right? 2 pi is 360, obviously. So you can say 2 pi equals 360. Then we have simple f frequency t time of observation theta is the phase angle of the signal, right? So these are the parameter introductions. So with that we are moving to the simple function of cosine, right? So here we have a sinusoidal signal, and this is the equation. In trigonometry, you know, uh, according to basics, if I say, if you have sine theta, right? Sine theta plus 90, right? Sine theta plus 90 is equal to cos theta. See whether you can remember this. According to the basics, sine theta plus 90 is equal to cos theta. Example, if you can remember, in general mathematics you were doing this. If you take 30 degrees, let's call it 90 degrees, sine 30 plus 90, sine 30 plus 90 is equal to cos 30, right? Is equal to cos 30. Sine 60 plus 90 is equal to cos 60. Likewise it goes. So these are some of the basics. So according to this, based on the basics that you know, right? Based on the basics, what you can further do is say if V is equal to this A, forget about A, we get sine omega sorry, sine 2 phi ft plus theta plus 90, right? 2 phi ft plus 90. So this is the other way around, right? 2 phi ft plus 90. You think about this 90. Here you have the 90. 2 phi ft represents theta, right? අපි මේකට ගමු වෙන එකක් theta ගත්තොත් it is going to definitely confuse you. අපි ගමු alpha, right? We'll make it alpha, right? So sine alpha plus 90 is cos alpha, sine 30 plus 90 is cos 30. Therefore you have sine 2 phi ft plus 90. Therefore this 2 phi ft is alpha, right? Is alpha. Then what happens? According to trigonometry basics, you can write V is equal to A, this time cos just 2 phi ft, right? You can write cos 2 phi ft. Sine becomes cos. Okay, sine becomes cos. Product. So there you go. Okay, so now this one is mathematically cos. You understood. A cos, A is the peak value. It is not going to change. A is the peak value. It was sine. Conceptually it was sine, but if you try to understand it a bit more in pure mathematics, from mathematics you have to call it cos, is because there is a mathematical reason. What is the reason? Here you see automatically with this phase shift, with this 90 degrees phase shift, mathematically we are getting a value for theta. So since it is 90 degrees, we have a simple theory when it comes to trigonometry. When you get a particular angle in sine plus 90, you can represent the entire part as a cos angle. So with that, this sine becomes cos. Other than that, there is nothing. It's still sine. So there is no any problem writing it sine 2 phi ft plus 90. No problem in that. But to make it bit more mathematical, whenever you see a situation like this, we can convert it to cos and write it down a little bit simply like this. Okay, students. So here, if you check the sine function, you have theta. So when it is in phase, theta is equal to 0. When it is in phase, theta is equal to 0. Right? So in phase theta is equal to 0. So then what you get is 2 phi ft plus 0. End of the day, A sine 2 phi ft. When you have a phase shift, 2 phi ft plus 90 becomes cos. So sine becomes cos. Then you get A cos 2 phi ft. Right? Okay. So let me take this picture. Then so if they move to the other page, group them. Sine wave in phase. Sine wave in phase is this. Okay. sine wave in phase is equal to plus 0 degrees. Therefore, you can say that and just 25 ft sine 25 ft. The summary, now this is the summary. This is where you get the connection, exact connection with Fourier series. So here you get it. This is how you get it. If sine wave with 90 degrees phase shift, right, with 90 degrees phase shift, what happens? This is how we write it. And with trigonometric basics, what you get is whatever angle plus theta plus 90 becomes cos, so you get cos 25 ft, right? Cos 25 ft. This is what happens. There you go. So this is the summarization, students. So instantaneous velocity, voltage will not change. Instantaneous voltage is not changing. This instantaneous voltage, plotting of instantaneous voltage, how that we plot, it is based on the peak value and the angular variation, how it varies. Okay, so this is the summary where we are having the direct alignment with the Fourier series. Now see, students, a sine 25 ft represents these sort of simple sine waves. A cos 25 ft represents these sort of sinusoidal signals. What is this sort? That is just a 90 degrees phase shifted sinusoidal signal. 90 degrees phase shifted sinusoidal signal. Now there can be a question in your head, thinking like, why only 90 degrees phase shift? Can't we have 180 degrees phase shift sinusoidal signals? Why can't we use 270 degrees phase shift sinusoidal signals? You need to understand that theoretically we can use, but in the practical case, um, when we try to mix 180 phase shifted signal, this is what happens, students. Right now, assume, let me take this one, right? Control C. Moving to another page. Now if we add, what I am going to show is, if we add 180 degrees phase shifted signal, see what is happening. Now what we are going to do is, don't forget, we are mixing this, right? We are mixing, we used to mix all this. Let's see. One second. Right, so let's see what happens now. Uh, so if I draw a line, right, see what happens. Now, if you think this line, hope everyone can see that I'm taking my tab lines. So you can see a tab line. Now assume I'm having a tab line right on the peak. If you can see, there's a tab line, dotted line on the peak. Just read the positive peak value and the negative peak value. That is exactly the same. Let's, for example, think positive 5 and negative 5. When you add these two together electrically, which is completely having opposite polarity, same value, positive 5 and negative 5, end of the day, what will you get? 0. So when you add these sort of signals, which is exactly having 180 degrees phase shifted signals, when you try to add them together, what happens is the result becomes 0. If I take the tab line further, at a point like this, again, in the first wave you see negative peak, assume negative 5. In the second wave you see the phase shifted wave, you see positive 5. At the same time instant, at the same time point, you see completely opposite, same value, negative 5 and positive 5. Then again it is going to give us a sum as 0. Sum is 0. Okay, sum is 0. So what happens if we use 180 degrees phase shifted signals? Most of the time what you all are getting is 0. So end of the day you don't get any results. What happens if you go for what do you call this, what the period can 270 degrees phase shift, 270 degrees phase shifted signal, see like this, 270 degrees phase shift, again the same, right? It is going to completely change, because when it comes to a situation like this where you need 0, where you need exactly 0, you get a peak value. Where you have exactly 0, you get a peak value, um, which is going to totally change, right? Which is going to totally change the fundamental signal. So when it comes to the periodic outcome, you will not be getting a guarantee always getting a periodic outcome. So the signal can be a non-periodic result. So normally we don't go for negative initiation. So in this case you can see at the initial point, the initiation is a negative peak value. It's a negative value. So we normally don't start negatively, either 0 or positive 90 degrees. Why that we don't go for 180? You saw that if you go for 180, definitely the top wave in phase is positive, the other part is completely negative, same value, so it is going to cancel itself and give a 0 value. Negative second half, negative half and the positive half cancels with each other, and end of the day answer is becoming 0. So 180 degrees is completely opposite phase, destructive interference, entire waves will be destructed. Negative, again destructive interference, we are not basically starting from a negative polarization, all the time we start from positive polarization, right? So normally in communication, that is why we are always sticking into only in phase signals as well as 90 degrees phase shifted signals, no any other phase shifted signals. So in Fourier, since it is periodic, don't forget we are still dealing with periodic complex signals. So Fourier series is for periodic complex signals, right? See in red color, it is highlighted in red color, periodic complex signals. So when it is periodic, we are making sure that we are limiting all our derivations only with in-phase sine signals as well as 90 degrees phase shifted sine signals, or we call it cosine signals. You don't go for 180 degrees phase shifts or 270 degrees phase shifts because we need a periodic outcome. But if you go for 270 degrees phase shift or any other different phase shifts, you will be getting a non-periodic outcome, as you can see here. See students, this is a non-periodic outcome. I will discuss it later. Okay, මේ වගේ result එකක් තමයි එන්නේ අපි වෙන වෙන phase shifts වලට ගිහිල්ලා ඒවා combine කරන්න ගියොත්. අපිට nice this, if you need this sort of an outcome or a square wave outcome, always we need to make sure that we are always keeping our alignment with the Fourier series. Okay, so again let me save this first, otherwise everything have to be again done as a repetitive work. So let me save it first for you all, yeah. And I'll share it with you, right? So to make it summarize, in communication, if the requirement is to generate a periodic complex signal, only in phase and 90 degrees can be used, right? Group it down. One 180 degrees uh, 180 degrees phase shifter signals can give us 0 due to destructive interference, right? Sorry, destructive interference, right? 180 degrees phase shifted signals can give us a 0 result due to destructive interference. You saw that, right? See, destructive interference. So end result is 0 all the time. In every time span, what you get, every time instant, what you get is a negative voltage and the same value positive voltage. It is going to be cancelled and give a result 0. Okay. uh, 270 degrees. Phase shifted signals. Let me say in 270 degrees phase shifted signals. Uh, uh, from the negative polarity. That will lead, sorry, lead the outcome become non-period. Become non-periodic, right? So due to these reasons, we are not going to use 180 phase shift and 270 degrees phase shifted signals uh, when we are mixing in the case of generating composite signals, right? So you have to make sure that. So here this bit gives you some brief explanation about why we are not using 180 and 180 and 270 degrees phase shift. That is this explanation here is just to provide an answer for a question that you get. If you have any, why the hell that we are only using 0 degrees and 90 degrees without going for any other? Because we need a periodic nice outcome, not an unperiodic outcome. That is why. Otherwise, we can go. Now, when we are talking, when I'm talking at the same instance through my vocal system, right, through the human biological vocal system, it is capable of providing many frequencies, many different frequencies simultaneously. So when I'm talking, what you all are listening is different frequencies at the same time span. So basically you are listening to a complex signal. You are listening to a complex signal. So in that complex signal, you need to understand it is not a periodic signal. Now what you are totally listening so far is to a complex signal which is non-periodic. The reason is the harmonics, then the frequency components, the phase shifting components, or everything is having in this particular voice signal is not quite theoretical. It is based on the practical phenomena. So definitely those are out of phase. Some are 270 and different other angles. So we cannot make sure that audio signals that we produce through musical instruments, maybe through speech or through some other noises, all those are non-periodic complex signals. But to become theoretic, to be aligned with the Fourier series and try to be much more into square waves, into periodic complex signals, because we need those signals to be generated in the case of fulfilling the data communication requirement. So when it comes to data communication requirement, what we need to deal with always periodic complex signals. So it is better to know what is the mathematical representation of a periodic complex signal and the decomposition of it. So that is where we are, but in the practical scenario, all the time we are always dealing with non-periodic complex signals when it comes to analog domain. Okay, when it comes to analog domain, voice is analog, right? Audio is analog, but data communication is quite specific, which is discrete. Okay, so that is where we have our discussion. So let me take you from the beginning. Just a simple sine function, v is equal to a sine omega t plus theta. When you are referring to content, you will see omega t. So you need to make sure what is omega. Omega is angular frequency when it comes to communication, not physics, not dynamics. Dynamics, it is angular velocity, but here it's angular frequency. Why? Uh, Based on degrees, how many complete cycles That is the idea. So omega is equal to 2 phi times f. We nicely understood what is it. Therefore, by replacing omega, you get a sine 2 phi ft plus theta. And here we have the introduction for each term. Simple function of a cosine signal. First of all, we need to graphically distinguish between a simple sine signal and a cosine signal. මේක අපිට මතකයි ත්‍රිකෝණමිතිය අපි ඉගෙන ගත්ත sin එක ඇන්දම 0 to 360 degrees දාලා අපි sin හොයාගෙන ගියා නම් sin 0 sin 45 sin 90 sin 135 sin 180 වගේ එහෙම හොයාගෙන ගියාම අපිට එනවා values. ඒ values අපි plot කරලා මෙහෙම යා කරපුවම මේක තමයි shape එක. We label the x-axis from 0 degrees to 360 degrees. Then cosine 0, cosine 90, cosine 180 කියලා හොයාගෙන ගියොත් අපිට මේ වගේ values එනවා. ඒක යා කරපුවම මෙන්න මෙහෙම shape එකක් තමයි ආවේ. So අපි කියනවා sine function graph, cosine function graph. That is in trigonometry. ඒ ඇවිල්ලා ත්‍රිකෝණමිතියේ. Communication වලදී අපි මේ දෙකටම කියන්නේ sinusoidal කියලා. Sinusoidal. These are sine waves. Sine waves, sine waves. Mode of energy transmission. Monad energy, electrical energy. This is electrical energy. These are sine waves. What is the difference? අපි මෙතන කියන්නේ මේක cosine අරක sine කියලා. Difference is the phase angle. Starting angular position is 90 degrees. So this is in phase, this is out of phase. එහෙම ගියාම having 90 degrees means the theta value will be represented by 90 degrees. The theta value originally you saw here is represented by 90 degrees. Api make a green color karot. If you make it green color, you have 90 degrees here, green. 9 degrees here, green. The potter api dena make. Because of that, you get cos. Sine becomes cos, right? Because of that, sine becomes cos. Hari इधर 90 degrees गया अभी basics दन्ना sin alpha plus 90 is cos alpha, sin theta plus 90 cos theta, sin 30 plus 90 cos 30. ये वगे इधर sin 2 phi ft plus 90 becomes cos 2 phi ft. Very simple. Then to make the long story short, if this is the sine, you get theta value 0. Theta value is 0. Theta value becomes 0 because the in phase, so no phase difference. Theta is 0, so you can finalize it as V instantaneous voltage equals peak times sine 2 phi ft. When it comes to cosine case, it is still sine with theta value 90 degrees, so it becomes cos. Sine becomes cos 2 phi ft. Then what I want you to take is a sine 2 phi ft, a cos 2 phi ft. Make a tamai ape conclusion nika. Now we'll move, since we have 8 minutes more, to Fourier. Nitin Fourier ge representation nika. So students, here in this second component, in this second mathematical component here, forget about the sigma. This sigma signature is always giving us the idea to take the summation. අපිට මේකේ sum එක ගන්න කියන්නේ. For n, apply 1 to infinity values and take the summation. එතකොට a n a1, right? N becomes 1 when n is equal to 1. Make a1 sine 2 pi times 1 times ft. The second part of it, if you have another sine component, next day we'll discuss it in detail. If you have another sine component, that will be n is equal to 2. So a2 sine 2 phi times 2 times nft. 2 times nft. If the n value is the third harmonic 3 times, fourth harmonic 4 times, likewise it goes. Likewise it goes. So now this bit represents the sine components. When the may wage sine components, the sine components you can see like this. If you are going to connect different sine components together, you will be having this Fourier series with this sigma. You will be having, if you are going to connect 3 sine components without having sigma, you have 3 these sort of pieces. Assume that you have a cosine, that means a 90 degrees phase shift representation. Then it moves to the cosine bit. You don't want to have theta value here. මෙතන theta එකක් දාගෙන පිස්සු නටන්න ඕනේ නැහැ sin කියලා දාගෙන. You don't want to struggle with the theta value, because automatically from this series it is given us a chance of directly applying it as a cosine value, because now you know the meaning. හරි, cosine උනේ කොහොමද කියලා දන්නවා. You know how it became cosine because of this 90 degrees phase shift. So if you get a chance of seeing a phase shifted signal component adding, you can pass all the parameters into the cosine part. So again here we have sigma, which is giving us the understanding. If we have many wave components, if we have many cosine wave components, accordingly you have to take the summation of all. So this sigma is giving us a message to take the sum. Other than that, nothing. Don't get frightened for these mathematical signatures. මේ සලකුණු වලට බය බීරාන්ත වෙන්න ඕනේ නැහැ. මේකේ meaning එක ඉගෙන ගත්තම ලේසි වැඩේ. So by now I hope you know, because you have learned maths up to the first semester. Now only you are learning the engineering mathematics. So anyway, I don't think that sigma is a big deal for you. Right? Even in your foundation, people who came from foundation, you must have been learning about sigma, and during the bridging also you must have been learning about sigma. So මේවා big deals නෙවෙයි. sigma කියන්නේ නිකන් signature එකක්. Why this infinity? That means Fourier is saying that උඹලට ඕන තරම් waves add කරන්න පුළුවන්. That is the understanding. You can add as much as waves that you have. Up to infinity means there is no upper limit. There is no limit of addition. That is the understanding here. Other than that, you don't want to find infinite number of signals and add them. There is no any other mathematical stuff to get done here. This is just a limit. So when you are decomposing, you will be doing the decomposition based on trigonometry, then based on calculus and limits. ඉතින් ඔය maths වල limits ඉගෙන ගන්නවා නම්, if you are learning limits in mathematics, if you are learning calculus, differentiation, integration in mathematics, that is for later use. ඒ දවස්වල මේව ඉගෙන ගත්තා නම් මේ දැන් පාවිච්චි කරන තමයි ඉගෙන ගන්න. So in signals and systems, you will be using those to decompose and see what are the components. Right, students? So this is what Fourier series is all about. මේ තියෙන sine components, මේ තියෙන cos components. Now I hope you know what is 2 phi ft and why that you don't have theta here. So because we understood it in this case. අපිට theta sine function එකේ theta තිබුණට, by having theta in the simple sine function, but in Fourier you don't see it. That is because of a fundamental reason. So we have reasoned it out in this word file. I will share this for your reference so that you can thoroughly understand. Then before we wind up, what is this A0? මෙතන A0 එකක් තියෙනවා. A0, just A. මොකද්ද මේ just A? Can someone tell me? There is no any oscillations, no any cosine ratios, sine ratios, or any other frequency ratios, nothing. Just A0. Can someone tell me what it represents? Just to check whether you all are in line with my explanation. What is A0? What is A0? අහගෙනද ඉන්නේ උඹලා මාත් එක්කද ඉන්නේ? උඹලා අහගෙනද ඉන්නේ ওই පැත්තට වෙලා? නැත්තම් shape එකේ මාරු වෙලාද? At least type, this is important. නැත්තම් you are going to struggle in the other module. Don't forget, that is true, you all are electrical and electronic students, but these parts are really needed, especially in power electronics. Sometimes in power calculations you will be having this Fourier transformation when it comes to three phase. I don't know but I hope that you might be having it. Then you will be having a chance of working in a signal processing scenarios, biomedical applications, then some other communication applications as electronic engineers. So you need to have this fundamental understanding, because for all these components you need to separately construct a an RLC circuit. So every frequency is governed by or generated by a specific RLC circuit. You call it a tuning circuit. Or you call it oscillators, right? Oscillators. So Fourier can be practically implemented by using many uh, oscillator. So oscillator, just an oscillator, it's a RLC circuit itself. So several RLC circuits. So here you have a RLC circuit for sine component. Then if you have 5 sine components, 5 RLCs. For sine components, different RLCs. So it's an array of RLC circuits or different outcomes based on variable capacitance. So in that case, you cannot get escape from this. So this is very, very important. Hari. So what is A0? Are you with me? A0 is the direct current component. Assume accidentally, if you have a direct current component, right, uh, working with your combination of the simple sinusoidal signals, if you have a direct current component, that has to be also, taken to consideration. So Fourier has given a chance to concentrate on the direct current components if you are having any. If you don't have, no problem, this bit becomes 0. But if you have, the voltage has to be considered, right? Voltage has to be considered. So we have a direct current component as well. Now students, what happens if the direct current component is there? What will happen if there is a direct current component? Right? If there is a direct current component, what happens is the wave is getting superimposed on that direct current, right? How to show that? You were learning analog electronics, transistors. I hope you were learning transistors. In transistors, what happens? When there is a direct current coming the collector, uh, emitter junctions, you know there is a direct current. When there is a base emitter, right, when there is a current flow in the base emitter, based on that, when the transistor moves to the active range, you get collector emitter voltage. That's basically a positive voltage. So then if you send an alternating current through base emitter junction, that alternate, according to that alternative variation, you will be getting an alternative variation on top of that DC component in the collector emitter, so that we can take the amplified outcome, right? So it is something like how to show that. So that is the problem. um, paste करो. Right now, අපි මෙහෙම ගමු like this. Now see, without the direct current component, this is the wave, right? It is fluctuated, or it is alternated across the zero voltage line. But if you have a direct current somewhere, a value like this, let's say 3 volts. This line here represents the 3 volts direct current component. Assume that you have it up to this point, right? මේ තියෙන 3 volts line එක. එතකොට මොකද වෙන්නේ මේ wave එක? This wave is going to climb up and alternate around or alternate across the 3 volts line. 3 volts direct current component. අපි ඒකට කියනවා superpositioning. මෙහෙම superposition වෙනවා. It is going to become a superpositioning. It is going to be superposition like this. මෙන්න මෙහෙම වෙනවා. අපි මෙහෙම ගමු. Right. Now this is superpositioning. Here this was this is 0 volts, this is 10 volts. So this entire the alternating signal is going to stay on top of 10 volts. The original wave input signal is superposition on a direct current component. This is what basically happens in a transistor outcome. That is why we call transistors are capable of amplifying the signal. So whatever a low voltage alternating signal that we are giving, when the transistor is in the active range, what happens? The low voltage or low level alternating current is going to stay on top of, it is going to climb on the high voltage direct current component in the collector emitter circuit, the collector circuit. So then we take the outcome with a greater level from 0 to here, it's a greater value. Because this peak is around, like, let me say 3 volts, but after superpositioning, if you try to measure it from the 0 line, you get the peak 13, because this is 10 volts and another 3 volts. So now the peak became 13 volts. From 3 volts to 13 volts increment, you call it amplification or gaining up the signal. Yeah, superpositioning, you know. Now you were learning about superpositioning. I hope while you are learning transistors, you know about superpositioning. එතකොට මේක තමයි ඒක නිකන් හරි අමතක වෙලා තිබ්බනම්, if you have forgot what is superpositioning, what I kept on explaining is that scenario. So when it comes to mixing wave components in the case of generating complex signals, if there is a direct current component in this mixture, what happens? The final outcome is going to be superposition on top of the direct current component, instead of oscillating across the 0 voltage line. It is going to be somewhere on top of a direct current. Because of that reason, considering a direct current component is very, very important. Okay, so now with the superposition, I hope you understood that well enough. Okay, if you have questions, let me see for your questions and answer. So here in Fourier, he didn't forget what you call direct current component, because it's a critical case. So we need to make sure that whether we have a direct current component or whether we don't have when it comes to mixing. Otherwise, it's a problem. Okay. So if we need the complex signal to be oscillate like this across the 0 line, we should not have a direct current component adding. But if you need a bit of amplification, better use a direct current component when you construct the complex signal. So now with this, you need to understand what are the components here that you see in the Fourier series, and end of the day, the S, the function of t. S is a function of t. What is this? This is the instantaneous voltage of the complex signal. Instantaneous voltage of the complex signal. In this you see V, simple V is the instantaneous voltage of the sinusoidal signal, the simple sine signal. Okay, but when it comes to complex signal like this, again what you can see, every instant the voltage keeps on changing. But this is not a simple situation, this is a complex situation. So in a complex situation also, we have a instantaneous voltage. So that is what you see here in the Fourier series as the subject We call it instantaneous voltage or instantaneous amplitude of a complex periodic complex signal. Okay, right? So it's one and this is about bandwidth and all. I will discuss those parts later. But the most important thing is to understand the Fourier. What are the components? Just a basic understanding, because you all are mathematically dealing with this later in this semester. But as a concept, having a slight understanding about what is going on with complex signals and how that it is aligning with the mathematical representation is the important thing. So that is the objective of today's discussion. I hope you learned something important. And the main thing is, please, before you go to sleep today, before you go to bed today, please make sure to go through the session again. If you are capable of downloading the video or at least playing it online, just go through the video again and go through the set of slides with the Word document that I'm going to share right after the session uh, before you go to sleep. Otherwise, during the sleeping process, what happens, your brain is going to automatically delete all the temporary information from your head. So when you wake up tomorrow in the morning, again your mind is refreshed. Most of the important parts might be erased, must have been erased during the sleeping process. ඒක හින්දා නිදාගන්න යන්න කලින් මේක පොඩ්ඩක් ආයි බලන්න to reconfirm it to the brain. So when it is in the sleeping process, if the brain identifies that the same point have been taken into account many times, එකම point එක දෙතුන් පාරක් use වෙලා තියෙනවා නම් they are going to keep it in a temporary memory. ඒක තියලා තියෙනවා පස්සේ ඕන වෙයි කියලා. They are going to keep it safe for some 2-3 days because it identifies that this were being used many times frequently. So that is what I'm explaining this. So please, before you go to sleep today, do a little bit of revision and go. So which will make sure that you can keep this sustaining this information sustaining in your head. That much important. That is one, right? That much important. Okay, so that's it for the day, students, and hope you found some important and as well as some good information today, and hope that it is useful for you. So I need your comments regarding the content today. There is no wait. There are Saneru. A0 is the base case where n is equal to 0, cos in both limits it goes from n is 1 to infinity. Yeah, but Saneru, yeah, you have came little bit near, but A0 is where we call it the DC component, and there is no any oscillations, so no any angular variations, angular representation, so there is no frequency. That is why you just get A and you have to call it direct current component, right? Furthermore, Jaivi has said that is the DC. Yes, it's correct, and there is no place define n is equal to 0 in the limit. Yeah, there is no n is equal to 0. It starts from 1 to infinity, so you need to understand, because we are dealing with integers, positive integers and negative integers. 0 is not an integer, it's a neutral value, so there is no chance of defining n is equal to 0. As you said, you are correct, Saneru. So A is not anything related to n is equal to 0. It is just because of it's a direct component where it doesn't have any variations, right? Okay, so you have got it. Apart from that, are there any other questions? සිංහලෙන් හරි අහන්න තව ප්‍රශ්න තියෙනවද? මොන හරි other content එක ගැන. The other message is, as I got to know from the admin, students doesn't have any more chance to download slides from the Teams, as I got to know. So I will pass all these documents to the admins. They will upload it to the system where you can download them by this evening. Okay, right after the session, I will send to Rashmika. She will distribute it among the system, so you can download all these documents from your account. How many of you are having issues with the system, like තියෙනවා නේද, delay in paying fees and all, එහෙම ප්‍රශ්න තියෙනවද? තියෙනවා නම් personally let me know. I can pass them through emails, right? If you are having problems in logging into the system due to what do you call this, late payments and all, that's not a problem to me. අපිට ඒක ප්‍රශ්නයක් නැහැ. ඒක that is just a operational issue, no? ඒක අපිට ඉගෙන ගන්න එකට ප්‍රශ්නයක් නැහැ. So let me know if you are having problems logging into your systems so that I can email it to you all. Okay, right? Any questions? Any more questions? Right, so please, as I told you, before you go to sleep today, make sure to revise the session again, because it's that much important. So we'll see whether we have any more questions. Right, no questions coming from your end, so I'll think that everything is fine up to now. Okay, students, so then thanks for staying up to this point with me. It's 4:15. We have done some extra work today, so let's meet up next day with some more content, right? Till then, be safe and be responsible. I'll meet you next week. Till then, goodbye everyone, take care.